Good afternoon, everyone. I'm Bingkun. I'm a postdoctoral researcher in University of Oxford, and I work with professors James Marrow and Peter Bruce. Today, I'd like to share our recent findings on the crack deflection in a multi-layered solid electrolyte in lithium metal solid-state batteries. So let's begin with an overview of the research background. So lithium-ion batteries, they are based on the organic liquid electrolytes, which are flammable and raise quite a lot of safety concerns in the practical application. In the contrast, the solid-state lithium metal batteries with a solid-state cathode, a ceramic electrolyte, and a lithium metal anode can fundamentally solve these safety issues and exhibit a significantly higher energy density. When charging this battery, lithium ions will be extracted from the cathode and transported across the ceramic electrolyte towards the lithium metal anode, where it is reduced to form the lithium metal. This charging is the reverse process. The lithium metal anode exhibits the highest energy density among all the anode materials. However, it is extremely difficult to achieve a fast charging for these anode materials. This is because the lithium filament will grow within this electrolyte, which will crack the electrolyte and lead to battery short circuits under a high current density. These lithium filaments are normally referred to as lithium dendrite, and the dendrite growth is one of the biggest obstacles for the application of solid-state batteries. So our group recently proved that the dendrite growth involves two separated processes, dendrite initiation and then propagation. The dendrite initiation is closely related to the microstructure of the electrolyte, especially the presence of the pores. Many of these pores, subsurface pores, can be connected to the exterior of the electrolyte through these macro cracks. When we're charging the battery, lithium will be plated to the lithium metal anode and preferentially deposit along this macro crack until it fills a pore. Further lithium deposition will induce a strength within this defect structure and also a pressure buildup within this pore. This pressure buildup will lead to the lithium extrusion back to the electrolyte surface through these macropores. And this viscoplastic flow of lithium will induce a hydrodynamic pressure buildup within this defect. When we're charging the battery at a sufficiently high current density, this pressure buildup may exceed the local fracture strength of the ceramic, and this will induce the electrolyte crack initiation in the form of a vertical crack below this pore. If we further depositing the lithium into this pore, the lithium will be deposited along at the lateral interfaces of this macro crack and induce a pressure buildup and leads to the crack propagation. So this is just a wedge opening mechanism for the crack propagation and dendrite propagation. So based on this mechanism, we can prevent the dendrite initiation in a 100% dense ceramics because there is no subsurface pores and macro cracks. However, in the practical manufacturing, it is very difficult to realize a 100% dense ceramic. So alternatively, if we cannot avoid the dendrite initiation, we can still prevent the battery short circuit by prevent the dendrite propagation. One effective strategy is to deflect the dendritic crack by adding an inner layer electrolyte. So to prove this, we designed this three-layered electrolyte structure by adding an inner layer electrolyte ceramic, lithium scandium chloride ceramic, in the main solid electrolyte, which is a sulfide type lithium phosphorus sulfur chlorine or LPSC electrolytes. We image the dendritic crack propagation by synchrotron X-ray computed tomography, or XCT. And this is this three-dimensional rendering is the XCT images of the pristine battery based on this multi-layered structure with the lithium metal anode at the top. During the test, we charge in the battery and we induce a lithium plating at the top electrode, which induces this cracks initiation, which is followed by the propagation of a transverse crack. And the crack will penetrate across the sulfide layer. When it reaches the inner layer, it is effectively deflected by the inner layer. This is very different from the behavior in a monolithic ceramic electrolyte. Right is a XCT cross-section image of a battery based on a monolithic ceramic, lithium, phosphorus, sulfur, chlorine, or LPSC. When we charge in the battery, lithium will be plated to the top lithium metal anode, which will induce a crack initiation, followed by a penetration of a transverse crack across the entire electrolyte without deflection. And this will lead to the battery short circuit when this lithium dendrite connects the anode and the cathode. So as a result, the batteries based on this monolithic electrolyte will be shorted under a current density of 3 milliampere per centimeter squared, which is far below the current density required for a 30-minute fast charging. In contrast, because of the dendrite deflection induced by the inner layer, solid-state batteries based on these multi-layer electrolytes will not be shorted under current density of 15 milliampere per centimeter squared, which will enable the fast charging. So this result indicates that the dendritic crack or the dendrite growth can be stopped by introducing such an electrolyte inner layer. And this will prevent the battery short circuit even under a very high current density. Now let's focus on the behavior of this dendrite deflection. These are the XCT cross-sections of two selected charging states. We can observe that the dendritic crack firstly deflects along the interface between the two different layers, and then it enters the inner layer, where it is further deflected within this inner layer. Now the question is, why does the crack deflect along the interface and also within this inner layer? First, let's consider the deflection within this inner layer. The XCT image cross-section of XCT cross-sectional image of the lithium scandium inner layer is colorized to enhance the contrast. The heterogeneous nature of this inner layer is very obvious. These orange regions are more X-ray attenuating, indicating that these regions are denser than their surroundings. So this suggests that there are numerous large dense particles separated by porous regions. And this microstructure is also apparent in this focused ion beam SEM cross-section, as shown in the red figure. You can also see these large dense particles. It also should be noted that these large dense particles are preferentially oriented with their long axis parallel to the interface between these layers. These dense particles will influence the propagation pathway of the dendritic crack. Indeed, you can visualize that the dendrite crack deflects along the boundaries of these dense particles. So we can conclude that it is these dense and stiffer particles with preferred orientation that deflect the dendritic cracks within this inner layer. Now let's consider the second type of deflection, which happens along the interface between the electrolytes. We replace the inner layer by a lithium germanium phosphorus sulfur, or LGPS, and also lithium phosphorus sulfur, LPS, and we image the dendritic cracks within the electrolyte by XCT. These 3D rendered XCT images show that dendritic crack can be deflected along the interface between the LPSC and LGPS, while there is no deflection when adopting LPS as the inner layer. So this says that not all inner layers can deflect crack along the interface. The biggest difference between these different layers is their Young's modulus. We measure the Young's moduli of these materials by nodal indentation. There is a close match between the Young's moduli of the LPSC and LPS, which is consistent with the observation of no crack deflection along their interface. The Young's moduli of the LGPS and the lithium scandium chloride are notably lower than that of the LPSC. This elastic moduli difference may affect the interface strength when fabricating these multi-layered electrolytes, because these multi-layered solid electrolytes are formed by cold pressing their powders under a 400 megapascal pressure. After releasing this pressure, synchronous XRD detects a residual tensile stress of 5 to 8 megapascals around the interface between the layers. This tensile stress will concentrate at the interface between the layers which exhibit dissimilar elastic moduli. And the tensile stress perpendicular to the interface will weaken the interfacial bonding. So compared to the bulk materials, this weakened interface may be more susceptible to to fracture when a crack approaches this interface. Thus, this deflects the dendritic crack. So we can conclude that it is the dissimilar elastic moduli between the different layers that lead to the weak interfaces where the crack will deflect. So we can conclude that the dendrite growth can be inhibited by the multi-layer solid electrolyte structure, and the crack deflects can deflect along the interface between layers with dissimilar elastic moduli, and the crack can also be deflected within the inner layer, which adopts a preferred orientation of dense particles. So these findings inspire further exploration of fracture-tolerant solid electrolytes by exploring other inner layer materials which exhibit dissimilar elastic moduli from the main solid electrolyte, and modifying the electrolyte microstructure by introducing stiffer inclusions with preferred orientation. Other deflection mechanisms, such as introducing residual stress within the solid electrolyte, can also be adopted. Finally, I'd like to thank my supervisors, Professor James Marrow and Professor Peter Bruce. This research is funded by the Faraday Institution. Thank you very much for listening.